Alright, so before we move on to derivatives, we're going to prove one final useful property of limits, and this has to do with limits when we're composing functions with one another. This one is that the limit of the composition is the composition of the limits. In other words, if we have two functions, f and g, and it's worth calling out here that f and g have both the same domain and range, and we want this guarantee because we want to be guaranteed that the output of g is actually something that makes sense for us to feed forward as the input into f. And we'll see how that comes up. So given these functions f and g, such that the limit as x goes to a of g of x is L, and the limit as x goes to L of f of x is M, then the composition f of g of x will approach M as x approaches a. And our strategy for this is going to be, once again, we're going to appeal to the definition of the limit, meaning we're going to find some delta that we're going to use to control the behavior of x. And what that's going to do is it's going to squeeze g towards L. And in doing that, it's going to squeeze f toward M. And this one is a pretty straightforward one, and you'll kind of see how that plays out. So again, appealing to the definition of the limit, we need to show that for every epsilon greater than 0, there exists a corresponding delta greater than 0, such that, guaranteeing that x is within delta of a, additionally guarantees that f of g of x is within epsilon of M. Okay, so let's take some epsilon, right? We already know that for every epsilon we can imagine, so long as it's greater than 0, there exists some delta. We're going to call this one delta f, which is also greater than 0, such that by squeezing x to being within delta f of L, we can squeeze f to being within epsilon of M. Ooh, there's a lot of letters to juggle around here. And why do we know this? Well, we know this because we're given in the provided guarantees of this proof that as x goes to L, f of x is actually limiting to M. Right? We've done nothing but write out the definition of the limit for f here. Okay, so now we're going to use this delta f. Now we say for delta f, there exists yet another delta g which is greater than 0, such that by controlling the behavior of x around a to being within this delta g, we can guarantee that g of x minus L this time is smaller than delta f. So the strategy here is, and let's just call out that this again is appealing to the fact that the limit as x goes to a of g of x is L. And we've, again, just written out the definition of the limit, except we've chosen a very specific epsilon. We're using, the strategy here really was use delta f as g's epsilon. And that was our key strategy here. Okay, and to complete the proof, we choose our final delta. We choose our final delta to just be equal to delta g. Now, notice what that means. So, say we guarantee that x is within our chosen delta of a. Well, obviously that means it's within delta g of a, because these two deltas are the same thing. But that implies that g of x minus L is smaller than our delta f. But knowing that we've now controlled the argument of f to being within delta f of a, remember that this controls the argument of f because it's g of x that we're feeding into f. This tells us that f of g of x minus m is smaller than our desired epsilon, which is exactly what we aimed to prove. And it's worth calling out that this can be written in a variety of ways. So when these limits exist, for example, we can say that the limit as x goes to a of f of g of x is equal to f of the limit as x goes to a of g of x, provided, of course, that this limit is defined, or rather, we probably shouldn't say that because that requires actually knowing what f is at L, but we don't know that. Instead, what I'm going to say is that this is just equal to the limit as x goes to L of f of x. And so we can substitute out the g of x for what we know it's going to approach, and that is this L here. And to carry this one step further, we can talk about a corollary of this mini theorem already that applies to continuous functions. So recall that the definition of a continuous function, or at least a function which is continuous at some point, is that if the function approaches exactly what its value actually is, then we say it's continuous. And to illustrate that a bit more clearly, let's imagine a function which for the most part is nice and smooth and curvy, but at, let's say, some given value a, it abruptly jumps up and takes some different value, leaving a hole here, but then afterwards it proceeds nice and smoothly. Now, this is an example of a function which has a value at a, has a limit at a, but doesn't quite fit with our intuitive notion of a continuous function being something that you can just draw without lifting your pen off the paper. And that's really what this definition of continuity is meant to capture. It's really a kind of a safeguard for us to avoid pathological examples like this one here, where we've arbitrarily introduced this discontinuity almost for the sake of being contrarian. So, carrying on, what we're going to show is that, let's say we have two functions which by themselves are known to be continuous. So g, we're going to say that g is continuous at a, meaning that the limit as x goes to a of g of x is, not L, but rather g of a. Let's erase this here. Good thing we caught that before we moved forward. Is going to equal whatever value g actually takes on at a. And again, we're going to correct our definition of f being continuous here and say that f is approaching whatever f actually is, this time at L. So, to going back and just saying this with one breath and no mistakes, we're saying that f and g are continuous at a and L respectively, meaning that as x approaches a, g of x approaches g of a. And as x approaches L, f of x approaches f of L. Now, if we want to reason about what f of g of x approaches as x goes to a, we can actually prove that we're guaranteed that it also approaches f of g of a. So that the composition of these two functions is itself going to be a function which is continuous at a. And this is more or less going to be a one-line proof here. So we know f of g of a is well defined because we can assume that g of a exists and that f of L exists. So this isn't going to be some pathological value. But is this limit going to converge to where we expect it to? Well, if we use our previous result, we know that the limit as x goes to a of g of x is g of a. So limit as x goes to a of f of g of x, and substituting our limit, right, we know that this equals the limit as x goes to g of a, which is what g is itself limiting to, of f of x. But that's just f of g of a. Using the fact, so this hop is because g is continuous at a, and this hop is because f is continuous at L. And the result is a function which is itself continuous at A, concluding the corollary. Next up, derivatives.